Today, my goal is just to help you get ready for that exam that opened this morning at 8 in the morning. And make sure that you feel comfortable with the ideas. The exam, I tried to get the late fee dropped, but the testing center is going to charge you $5 if you come after 2 o'clock tomorrow. So if you come today, you don't pay anything. If you come tomorrow morning before 2 in the afternoon, you don't pay anything. After 2, they're going to charge you $5. I don't get that money. Okay, that doesn't come to me. You're not going to be able to write on the exam, so you should bring some scratch paper with you. And we've seen problems where we've had things moving along a grid, pulses moving along a grid. And so I would suggest that at least one of your pieces of scratch paper have these grid lines so that it'll make it easier for you to draw your pulses. Okay, questions on the exam? 25 questions, each worth 4 points. Gonna be fun.
They're all multiple choice.
What's that?
They're all multiple choice.
They're all multiple choice. Yes. Believe me, folks, when I came here 2.5 years ago, I had half multiple choice and half long answer. And I was used to just having all of my staff come grade into the night. And the difference here is that at Montana, I had 15 grad students that their job was to help me grade those exams. And here I've got a whole bunch of undergraduates, very, very talented undergraduates, but they've got their own classes and their own homework that they got to do, and they're volunteering their time. So I found that I was ending up in a room alone with 500. You cannot believe how tall a stack of 500 exams looks at now 11 o'clock at night. And so that's why I moved to multiple choice. It's not ideal, but it's what I can do. Today, we're going to practice a lot of different concepts, but I also want to just kind of review that second tutorial and make sure that everyone came away with the right understanding there. So some announcements. The test will cover simple harmonic motion, waves, and sound, including the last tutorial. Homework solutions are at the max site. 2 exam solutions are at the max site. And I sent out an email with links to 2 review sessions, one that happened in fall of 24 and one that happened in spring of 24. So if you are still struggling with some of the ideas, you might look over those review sessions. Let's start quickly. Someone asked me about one of the questions in a sample exam where sound was going from air to water or water to air. And let's just imagine what that's like. We know that in gases, the sound moves as particles just race across and smack their neighbor, and then that neighbor smacks its neighbor. It's kind of like how gossip moves across town. Okay, you got to run and tell your neighbor. Now, it's faster in liquids than solids. In liquids, we've got more connection between the molecules. And so it's kind of like gossip when you've got phones, okay? Sound traveling in air is like the old day gossip. And then we got phones and we can really get it across. And then in solids, it's like the internet. Now we can tell everyone. Okay. So what we see from this table is that in air at room temperature, we've got 343 meters per second. In water at the same temperature, it's going 4 times faster. And in steel, it's going 11 times faster. Okay. In steel, you've got that lattice work. And so you jiggle one of those atoms and it's jiggling the lattice work. Okay. So if let's say I go out in a boat and I want to call my friend Flipper the dolphin. And so I take an air horn and I aim it straight down at the water and go, okay. And I send the signal, come see me. Okay. And the question is, as that sound wave passes from air into water, where the wave speed is about 4 times faster, what changes and how? The wavelength, the period, the frequency, how do they change? So let's quickly look at that. I hope what you're seeing there, I hope by now you have seen that those lines are the wave fronts. Those are the compressed regions. In terms of the transverse, they would be the equivalent of the crest. Okay, a visual would be something like that, where these places where the molecules are bunched up, those are the wave fronts, and they're moving down towards the water. Now, again, we saw this before. Individual particles aren't moving very far away from their equilibrium. It's the energy and the momentum that's moving in those wave fronts, the crests. Okay. Now, if I watch as that wave approaches the water, and then it reaches the water, and when that first wave front crest hits the water, I'm going to start counting. I'm going to set some imaginary lines and put a couple of Walmart greeters up there with their counters, and they're going to count wave fronts as they go past. And so this one hits the water and it takes off. Okay. And then this one hits the water and takes off, and this one hits the water and takes off, and this one hits the water and takes off, and this one hits the water and takes off. Okay. What you're noticing is what we've already discussed before, and that is any wave has the same frequency as the disturbance that causes it. In this case, it's the wave in the air. That's the disturbance that's causing the wave in the water. And so they have to have the same frequency. If one is a wave at 100 hertz, so is the other. What's different, however, is that wavelength. Okay, the frequencies are the same, but the wavelength, if I've got to get 4 times further down the road in the same amount of time, the same period, I have to have a wavelength that is 4 times longer. Okay, so if I go back to my original question, the wavelength has to get longer by a factor of 4 in water. The period, the time it takes for one oscillation, is the same, and hence the frequency, which is 1 over the period, would be the same. Talk to your neighbor, see if your neighbor is okay with that.
Oh wait,
Like right after.
I'm usually in the afternoon section, but I can't do this. How does that stand? I know a couple of them are dropped.
Yeah, like you think of the wavelength.
We'll see. That's the only reason why they couldn't. Or else I would just take it right now. That's the spring one.
Okay.
And like,
I don't know. Let's just go.
Water.
Yeah, it was like, it's like, what is that?
You had some problems like this in the tutorial. And I sent some guidelines, some hints yesterday in an email. The question is, did the mother pulse that created these twins, did it come from the left or from the right? Okay, remember, in these problems, it's always about an incident pulse, a mother pulse. The start. Coming into a boundary between two springs or any two medium, where the speed is different, where one's fast and one's slow. And what we find in all of those cases, whether it's electronics or whether it's springs that we did in the tutorial, is that the mother pulse dies at the boundary. Okay, sad tell. And in that death gives birth to twins that race off in both directions from the hospital. Okay, and so I look at that and I see the twins. Those are the twins. Which one got furthest from the hospital in the time that it took for me to take this picture? Yeah, the blue one. Okay, so I know that the blue spring is the fast spring and the red spring is the slow spring. Okay. Now we know that on a spring or wire, we know that it's the heavy spring or wire that is slow. Why? Well, that's this equation here. We know that because those two springs are pulling on each other by Newton's third law, which you learned in physics 105, the tension has to be the same. And so whichever one has the bigger mass density, the mu, if it's in the basement and it's big, that gives me a small value for the speed. Okay, does that speak to everybody's soul? Okay, so the heavy one is the slow one. Now, if I have a pulse come in on that heavy spring and hit the boundary, that's the mother pulse. That's the incident pulse. That's the one that started everything. Okay. Now, when she hits that boundary, what's the transmitted pulse? And the transmitted pulse is the one that keeps going, transmits into the other spring. Okay. Is that going to be on the same side or the opposite side? With your clicker. Oh, okay, now you can click.
Big to thin. Not then so they stay on the same page.
No matter what for the transfer.
That goes through. It's always on the
That it would act as well.
It'll actually go
Fast.
get in there.
Always on the same page as the
Yeah, you're gonna have to track too.
Yeah, it's going back.
Okay, last call. Get your vote in.
I'll watch this, guys. And then this
Last call. Okay, you said same side, except for 8 of you. Okay,
Question.
so every time or just this time? Every stinking time. Okay, there are no exceptions. No exceptions. It's always on the same side as the mother pulse. The transmitted one is the easy one. It never gets inverted. Never does. Okay, I have a slow spring, not a spring, it's a wave machine. And I have it connected to a fast wave machine here. They're coupled together right there. If I send a pulse down the slow side, just concentrate on the transmitted. Don't worry about the reflection, just the transmitted. It was on the same side. It was on the, this was up, that was up. Okay, now let me send it the other way. Let me send it from the fast side. It was up, same side. Every stinking. Okay. So, same side. Now, what about the width? What about the width of that transmitted pulse? Is that going to be narrower, same, wider, or I'm not sure? Go ahead and click.
Well, right. Narrow. You guys are-
Like, I like this one as a plus. And it can like. Low. Just get up and stretch it. That's really. That's back. Grant. Like a circular hover track, you can bar on it.
Okay,
Stop.
get your vote in. Last call. Okay, we said wider. Okay, most of us said wider. Okay, and that is the correct answer. But why? Okay, but why? Now, that was one of the main points of that second tutorial. It was the second page of the tutorial. And what we did is we represented that one pulse by two little pulses, one that was at the front of the original pulse, one that was at the back. But I also tried a different approach in the tutorial video. Let me try it again here. Let's represent that pulse with a school bus. And this is one of those magic school buses that you see on Sesame Street or whatever, the public broadcasting before we did away with that because it was communist. I love Sesame Street. I love all of those shows. So anyway, I don't know why they got rid of it. So this magic school bus can stretch, it can compress, whatever it needs to do. Okay. And so if we think of that going from a slow medium, like a dirt road that's all rutted and hard to get through, to pavement, what happens is that the front of that bus gets to the pavement first and speeds up. The back of the bus is still back in the dirt, going slow. And as a result, my school bus stretches and I ended up with a bigger school bus. Okay, and it represents the pulse. And so what we get is a pulse that is wider than the original mother pulse. If I'm going into a fast medium, if I'm going into a slow medium, it gets shorter. And you saw that here. Again, just concentrate on the transmitted pulse. I have a small pulse, not narrow, and then it gets very wide. Okay. And if I send it the other way, I start with a wide pulse and it gets very narrow. Okay. The magic school bus. Now, what I don't want you to worry about is the amplitude, how high it goes. That's messy. That's ugly. That's some mathematics we're not ready for. Now, I can say that the reflected pulse is always going to be a smaller amplitude than the mother pulse because they're on the same spring. And some of the energy went into the other spring. But that's all I can say. And I would never test you on that. Okay, so don't worry about the amplitude. Just worry about the width. Okay. Now let's talk about the reflected pulse. Okay. When that mother pulse hits that boundary between the slow on the left and the fast on the right, is the reflected pulse going to be on the same side or the opposite side? Again, with your clicker.
Okay. Yeah.
Blue.
It's always. Let's see me reflective pulse. Oh no, yeah, no, I'm just imagine
That
Yeah,
Gonna hit a boundary.
act like a free end.
Okay, last call.
Besides,
Get your vote in.
besides less heavy.
Okay, I'm setting it down.
We'll go higher and then.
On the same side, on the same side. Good. Oh, no one chose watermelon. Good. Okay. Same side is the correct answer. Is it always the same side? No or heck no? Heck no. No. Okay. If you're going from the heavy to the light, again, think of the heavy as a massive spring and the light as a fishing line. Okay. It's going to act like a free end. And we found in that first tutorial that when you bounce off of a free end, it doesn't invert. It doesn't invert. On the other hand, if I were to send it in from the light to the heavy, when it comes in on the fishing line and hits that massive chain, suddenly it's acting like a fixed end. And then it would invert. It would invert. Okay. Now, let's consider that reflected pulse and ask what shape is going to come away if I send in this mother pulse. Am I going to get a reflected that comes back like that or one that comes back like that? Tell your neighbor.
Gonna be on the exam. Remember that one?
Okay.
Yeah,
I hope what you remember is that the leading edge has to remain the leading edge. And by leading, I just mean out in front of the chart. Okay. This mother pulse is moving to the right, and this one is out in front. This reflected pulse is moving to the left, and the same part of the pulse is leading the charge. And that's because these pulses, when they meet the boundary, they don't all back up together. When they meet the boundary, the front turns around like a snake while the back is still going towards the boundary. Okay, it wraps around. That makes sense? Okay. And that was the answer to one of your homework problems in the tutorial. They came away with different leading edges. Okay. Now, I've got a handout here, an old exam question. And so I need helpers. Where are my helpers? Over here? You look like you're a helper, sir. Okay. Another helper over here. Thank you. Appreciate it. And there's my other helper. Thank you. There we go. Go where all the problem people are.
Yeah.
Like.
Rowdies.
So chill. As long as you not before that shit straight.
Just why you're a better seat.
Sitting there and then watch it. I kind of like
I'm sure.
Maybe it was I already don't know what this means.
Okay, thank you. Raise your hand if you don't have one. Anyone still need a? Two there. Okay.
My pen is.
Yes, sir. Question, okay.
Wavelength.
I'm sorry?
Wavelength of the.
No, thank you for asking that question. The width of the reflected pulse does not change because it's on the same spring as the mother pulse. Okay, and so as that mother pulse turns around and goes the other way, it's always traveling the same speed, forward or backwards. Okay. Now, I have a feeling, a strong feeling, a premonition that you're going to have a problem just like this on exam A. And then you're going to have a problem just like this on exam B. Okay? It's a feeling. Okay? So let's figure out how to solve this. Some of you have already figured out a shortcut. Okay? But I'm going to go through a little bit longer way, and then we'll talk about the shortcut. Okay? So, first of all, we've got to recognize that those are the twins. We didn't give you a picture of the mother pulse. Okay? That's what we have to figure out. Where did the mother pulse come from? The left or the right? Okay? So, the question is, which of those pulses is on the fast spring and which is on the slow spring? Considering that these twins were born at the same instant, midnight, at the same location, the hospital is right here at the boundary. Which spring is the fast one? The blue one, okay? The blue one. And the red one is the slow one. And I can see that by how far they got away from the boundary by the time I took this picture. Okay. Now you're told in the problem that one spring is made of steel and one is made of brass. And you're told that the steel spring has a larger linear mass density, the mu. The mu is bigger. And so if I ask you which of those springs is the steel spring, you're going to say, well, it's a slow one. It's a slow one on the right. And so I'm just going to kind of give us a reminder that that's the slow one by making that nice and fat. Now, folks, I got to tell you, some of us were confused on the tutorial homework because one of the springs was drawn dark and one was drawn light. And we immediately said, well, the light one must be the light spring. The light one was a light color. That's different than a light mass, okay? So you have to use something other than color to indicate whether it's fast or slow, okay? Because Greg on the exam isn't going to help you out there, okay? He's just going to make one green and one purple. Now, the question is, which is the reflected pulse and which is the transmitted pulse? Now, again, there's a shortcut that we can take, and we'll come back to that. But before we do, let me just point out that there's only two possible answers. And this is true of a whole lot of questions in physics. You remember the Billy and Elaine question. Which one had the higher frequency buzzer? It's either Billy or it's Elaine. There's only two possibilities. When you have a question like that, rather than sit there and stare at the question for 30 minutes, wondering where to go, reach in your pocket, take out a quarter, and flip it. Heads is one answer, tails is the other. Okay? What I'm saying is guess and check. Because even if you guess wrong and you find that you guessed wrong, you know the right answer. There was only two. Okay, so let's guess and check. I'm going to guess that mother pulse came in from the left, from the fast spring. Okay, so which of these would it possibly be? Which would be a candidate here? Could it be this one here? No or heck no? Why?
Leading edge is different.
Wrong leading edge. Okay. This, if it came in from the left, if the mother pulse came in from the left, that would make this the transmitted pulse. And the transmitted pulse always looks like the mother pulse, except for the width. Okay. And so that one can't be. Okay. Now let's talk about this one. This one would give me the right transmitted pulse, but am I meeting a fixed end or a free end when it hits the slow spring there? What would it be? Yeah, it's acting like a fixed end, okay, going from the fast to the slow. And so that means this mother pulse, when it reflects, is going to invert. The leading edge will still stay the leading edge, but it's got to invert. And that's not what we saw in the original problem. So this can't be the mother pulse. Well, what if I started out on the bottom and then it hit the boundary and it flipped? Well, that gives me the right reflected pulse. What's wrong now? Yeah, it's going to give me the wrong transmitted pulse. It's going to give me something that's also down. And so that can't be right. So I have tried every possible combination of mother pulses coming from the left. What that tells me is I guessed wrong. I guessed wrong. So let's bring it in on the other side. If I bring it in from the slow side, is it going to be meeting a free end or a fixed end? A free end. And so that means the reflected pulse is going to come back on the same side with the leading edge still the leading edge. And the transmitted pulse always looks like the mother pulse and just different width. And so that worked. That worked. Now, some of you are saying, oh, Greg, that was a waste of my time. Okay. That was 5 minutes I'll never get back. Because you've already seen the shortcut. And that is the transmitted pulse never gets flipped. The reflected pulse does get flipped if you hit a fixed end. And so if I have the twins on the same side, both up or both down, I know the reflected pulse didn't get flipped. That means it had to come in on the slow spring, on the heavy spring. If, on the other hand, one's up and one's down, and it doesn't matter which is which, the reflected pulse had to get flipped. And that means the mother pulse came in on the fast spring and hit a fixed end when it met the slow spring. See if your neighbor's on the bus, people. Check for your neighbor. Okay. Let's Let's try to see that on these two wave machines. And I just want you to look right after the mother pulse hits the boundary. Because once it gets to the ends and starts bouncing back and forth, it's all crazy. But if I come in on the slow, and what I get is the reflected comes back on the top and the transmitted goes forward on the top. If I send it down, the transmitted is down and the reflected is down. If I send it from the fast side up, the transmitted is up, but the reflected comes on the bottom. If I start with the fast side down, the transmitted is down, but the reflected was up. It got switched. Yes, Thomas.
Can you help me out to understand the amplitude? Because you were saying that the reflected pulse is just a bit smaller than the incident pulse. So why here is the transmitted pulse smaller than the reflected? And is that even?
Oh, what I'm saying is that I can say something about the reflected pulse because it's on the same spring as the mother pulse. Okay. But the transmitted pulse, I can't say anything. Because if you think of that, again, go back to that cartoon in your head where you've got the two springs, one a bunch of football players, and then a boundary, and then a bunch of ballerinas. Okay. We get to the last football player. He's pulling like he's going to pull a football player. And there's a ballerina. Whoa. Okay. And so suddenly that amplitude can be bigger than the original mother pulse. But if I'm going the other way and the ballerina goes to lift another ballerina and there's a football player, then I'm not going to get much.
So if the two amplitudes are different, can we see any trick or?
I'm sorry?
If the two amplitudes are different, can we see any trick or is there any trick with the two different amplitudes? If they're different, does that mean something?
No. Just don't even worry about the amplitudes. What I'm saying is you have so many important decisions to make in your life. This ain't one of them. Okay. Okay. Concentrate on your relationships. Okay. Yes, in the back here. Just a second. Old man coming. No, I have a in this picture it was, but it can be either. I just made one shallow and one steep so that we could tell them apart. Okay, but whatever one is leading the charge has to still be leading the charge when it turns around. Okay, so I could have sent the steep side in first, and it would have been the first one to leave. Okay, now let's change gears. In the first tutorial, we talked about pulses that would meet a boundary, either a fixed or a free boundary, and what happened as it was bouncing off. And in that case, there's no such thing as a transmitted pulse. There's only one spring and one wall or one boundary. Okay. And so what we did is we used a trick. If it was a fixed boundary, we pretended that there was another pulse coming from the other side, inverted, passing through. And if it was a free end, we pretended there was another pulse coming through on the same side. Now, in doing that, we had to use superposition, and that was kind of a theme throughout both of the tutorials. And what that means is that when two pulses meet each other, we just add them up as they pass through, okay? And we know that we can't actually have a pulse that has sharp corners like that, but those are the ones that are easier to work with mathematically. And so we'll do that on the exam, and you saw that on the homework. Now, as these two pulses approach each other, once they overlap, now I have to use superposition. And so I say, on the left here, I've only got the green. But here I've got 1 unit up on the green and 1 unit up on the red. That's 2 units up. Here I've got 1 unit up on the green and a half on the red. That's 1.5. And then I just have the red. And that's what the pulse or the spring would look like as they are passing through each other at that instant of time. Now, again, that looks very unlikely. Boy, I don't think I've ever seen a spring look like that. And that's because the pulses we started with were very unlikely, okay? Now, if I let them overlap like that, and I use superposition, now I've got 1 on the green, 1 on the red, that's 2. And then here I've got 1 on the green, but none on the red. And so the spring's going to look like that. And then when they get here, I've got the red on the left. And then here I've got 1 on the green and a half on the red. That's 1.5. Here I've got 0 on the red and 1 on the green. That's 1. And then it's just the green. And that's what it would look like. And then they pass through each other like ships in the night, going on their way. Okay? Check that your neighbor is going to be able to do that on the exam, and remind your neighbor to bring wrapping paper so that they can. Just get that out.
I've been training for this. January. Spots and it's like it should be.
Okay. So let me run through some other sample problems that you can expect on the exam. We spent some time in the homework talking about these mass on a spring problems going back and forth. And you remember I promised you that those problems where we used energy, I would stick with horizontal problems on a frictionless table. I wouldn't do the vertical ones for the energy problems. And so again, I have a feeling that you're going to have a problem like this on the exam. A 4 kilogram block is fastened to a spring with constant K value of 200 newtons per meter and is oscillating horizontally on a frictionless table with amplitude of 0.3 meters. What is the block's speed when it is 0.1 meter from equilibrium? Now, you remember you've got these 3 equations. The general equation is that the total energy is the energy, kinetic energy in the motion of the block, plus the potential energy in the spring. And that always applies. And then we know that a turnaround it's got to stop to turn around. So there's no energy in the motion, and all of the energy is in the spring. At turnaround, V is equal to 0 and delta S is equal to the amplitude. Okay. And then at equilibrium, on a horizontal system, the spring is neither stretched nor compressed. Delta S is 0. And so that means at equilibrium, V is equal to V max and delta S is equal to 0. And so this is going to be equal to 1/2 mv V max squared plus 0. Now, the first step in these problems, whether you're offered any points or not, is to find the total energy. And I look at what I know here. I know the mass. I know the spring constant. And I know the amplitude. And come heck or high water, I got to find that total energy. And I see that I've got everything I need to find the total energy with this version of the equation. And so I would say the total energy is equal to 1/2 kA squared is equal to 1/2 times 200 newtons per meter times 0.3 meters squared. Remember to square that. And folks, I'm an old man. And over again, I see that the people that get this wrong are the ones that don't square that. And you know that I'm going to go through and figure out what the answer is without squaring it. And that's going to be one of the options, right? Because I'm evil. Okay. And so this gives me 9 joules. Well, now they want to know how fast is it going when it's 0.1 meters from equilibrium. Well, I'm not at the turnaround point. I'm not at equilibrium. And so I have to use the general equation. Okay, so I go and I say E total is equal to 1/2 mv squared plus 1/2 k delta f squared. This is going to be 9 joules is equal to 1/2 times 4 kilograms times v squared plus 1/2 times 200 newtons per meter. And this is 0.1 meters squared. 0.1 meters squared. And this gives me a V of 2 meters per second. That's just algebra, right? That's just algebra. Okay. And there's the answer right there. Make sure that your neighbor knows how to get from here to here. Okay.
Don't worry about it.
Okay. Questions on that? Okay, doke. We found 2 separate ways of finding a spring constant, the static approach and the dynamic approach. And I told you that we would be testing for those approaches on the exam. So you should be ready to do either of those or both of those. And with the static approach, I exert a force on a spring, usually by hanging something on it, and I use Hooke's law. So in this problem, we said that if we put a force on the spring of 20 newtons, I get a stretch of 0.2 meters, 20 centimeters. And that gives me a K value of 100 newtons per meter. And then I said, well, what if I bounce a 4 kilogram mass on that. Okay. And this was an old exam question that caused problems because some of them were saying, well, if I hang a 4 kilogram mass on that spring, the force on the spring isn't 20 newtons, it's 40 newtons. Yes, that's true. But there are two sentences there. Okay. The first sentence says, if I pull on that spring with 20 newtons, it stretches this amount. Okay. And then we take that same spring and we put a 4 kilogram and we bounce it. And we want to know what's the period. And here we would use the dynamic version. Where I've got this equation, m over k. And so I would just plug in 2 pi square root of 4 over 100. The square root of 4 is equal to 2. So that's going to be 4 pi. The square root of 10, 100 is 10. And that's going to be 1.26 seconds. Okay. So the answer on the exam would be 1.3. How we doing? We okay? All right. Hey, this test isn't going to be that hard. It's going to be piece of cake. Piece of cake. Okay. A periodic wave on a string is observed to have exactly 2 cycles in 3-meter section of the string. The crest moves at 20 meters per second. What is the frequency of the wave? Again, I put this up there because this is an old exam question that caused problems because people were essentially spinning their wheels asking, what's a cycle? What's a bicycle, tricycle? What do we got here? Okay. A cycle is a repetition. In space, it would be a wavelength. In time, it would be a period. Okay. In this case, we have these cycles in a 3-meter section of string. We're talking about a repetition in space. That means the wavelength, I got 2 wavelengths in a 3-meter section of the string. And so if I go to this grand high equation, I'm told that the speed is 20 meters per second. I just figured out that the wavelength is 1.5 meters, and that gives me a frequency of 13.3 hertz. Okay. Now, maybe this is a good time to talk about the equations. Okay. I think some of us are not seeing the big picture when it comes to the equations. This is the grand high wave equation. It works for all waves. Standing waves, traveling waves, transverse waves, sound waves, longitudinal waves, all waves. If you're looking at standing waves, it applies to every harmonic. Of course, if your system has a node at one end and an antinode at the other end, these would not exist. But if you have ends that are the same, you'd have all of the harmonics, and that equation would work for each and every one of them. And you'd get exactly the same value for V in each of the harmonics. Okay. This equation, the next most important, the number of footballs times lambda over 2 is equal to L. That works for all standing waves. And then you've got 2 more equations for V. Okay, I can always get V from this equation, but I can also get V from this equation if I've got a transverse wave. And it could be a traveling wave or a standing wave as long as it's transverse. And by transverse, we mean on a spring or a string where it's perpendicular to the motion of the wave or pulse. Okay, and then for sound, it's simple. 343 meters per second. Done. Okay. And those are the equations that are going to solve these wave problems. Yes, sir.
We can use the calculator.
What?
Asking you. Calculator.
What that?
Can you use a calculator?
Yes, you can bring any kind of calculator you want, as long as it's not breathing. Okay. Okay, other questions? Okay, here's a hard one. Here's a challenging one. Okay. You've got a tube that's open at one end. And that has some length L. And we cut it into two shorter lengths. Okay. Okay, and I'm going to call this length closed because it's closed at one end. And I'm going to call this length open because it's open at both ends. Okay. And we find the fundamental frequencies of the two pieces. One has a frequency of 425, and that's this one here. And the one that's closed at one end has a fundamental frequency of 675. And we want to know is what's the fundamental frequency of the original two? Okay, so with your clicker, no, there's no clicker on this one. With your neighbor, figure that out. What do you got there?
I guess
Divide by both.
Yeah. Yeah.
It's on the sound, right? Length of this one is a half. That length.
Somewhat.
Or another length. But then it's and so. I was gonna use this principle. Those two have together and it's. Yeah, the two of them.
Yes, let me try it.
Use that length. That one.
The closed one, there's a hole to fall. Because fundamental
That's the word.
big. So we're gonna.
Okay. The first thing we want to do is find the wavelength in these different tubes for the first harmonic. In the closed tube, lambda 1 is going to equal the speed of sound over the frequency one, that's going to be 343 meters per second over 675 hertz. And that's going to give me 0.51 meters. That's lambda 1. In the open tube, my lambda 1 is going to equal, again, V over frequency 1, 343 meters per second over 425 hertz. And that's going to give me 0.81 meters. You notice we just used this grand high equation. Now we're going to use this equation. But I don't really need to. I could, but we know the answer already. In the closed one, we have half a football, and we multiply that by lambda over 2, and that gives me the length of the closed. Well, what that gives me is that lambda 1 for the closed, let's do this. The length of the closed is equal to lambda 1 over 4. Well, I knew that already. I only have a half football fitting in there. It takes 2 footballs to make a wavelength. And so if I want to know what this length is, it's going to be 1/4 of my wavelength. That's going to be 0.51 meters over 4, and that gives me 0.128 meters. Okay. And then I do the same thing over here. Number of footballs, I have 1 times lambda over 2 is equal to L open. Well, that tells me that lambda L open is equal to lambda 1 over 2. Well, again, I know that just from my picture. I have 1 football that fits in there. It takes 2 footballs to make a wavelength. I've only got half a wavelength. And so this is going to be my 0.81 over 2, and that's going to be 0.405. Okay. Now, the length of the whole tube is equal to the closed length plus the open length. And so that's going to equal 0.533 meters. Are you still with me? Okay, I just added these 2 numbers together, and that's what I got. Well, now I know that the lambda for the total, let's call this the total, when it was blowing at the first harmonic of the original pipe, I only had half a football there, and that's 1/4 of the wavelength. And so that means that the wavelength is going to be 4 times that total length. And so if I multiply that by 4, I get 2.13 meters. And now I go back to my grand high equation, and I say that the frequency of the first harmonic is equal to the speed of sound over the wavelength, and that's going to be 343 meters per second over 2.13 meters, and I get 162 hertz. Okay, and that's the answer. Now, folks, I want to make you a promise right now, and that is that problem is too hard to put on an exam that you're taking 25 questions on, okay? But you notice that I just kept doing the same thing over and over again. I kept using the wave equation, and then I compared the length of the tube to the wavelength. That you can do that. Yes. What that? Where I get the 4 from? I'm trying to compare.
I remember, right?
in the original tube, I only have half a football. That's 1/4 of a wavelength, because it takes 2 footballs to make a wavelength. Now, if I wanted to use the wave equation, I would say number of footballs times lambda over 2 is equal to L. The number of footballs is a half. If I solve that for lambda, I get lambda is equal to 4. Okay, folks, let's stop here. Good luck on that exam. Go take it. Go take it now.
But it made so much sense in my head.